already started to talk about the building. There used to be 5 chimneys, or 5 fireplaces rather, if you can imagine, and you can see these windows up here they're not original, but they're actually copies of the original windows that were made by the previous owner. So he hand built all the windows to match. The 2 in the front room downstairs are original. So original panes and sashes, not original glass, because this building was about 70 years old when the Halifax explosion happened, so would have lost all the glass. In a passive house, windows kind of make or break you, and so I'll talk a lot about like the great windows that we're going to be installing. Some of you are brave enough to go into our basement. So it's got, rough fieldstone walls and questionable moisture passage through the building. So ultimately we will be insulating that space, but we're not going to do anything right away because I want to really get a handle on what the heck's going on down there before covering it all up. It just doesn't make sense until we really understand it. So we do have, or I have a working plan for that, but it's a TBD. And then we have a party wall, which adds some complexity. So this wall is, we're adjoining the building next door, and so that makes things a little bit trickier when you're thinking about a retrofit. A little bit easier too for passive house because you're not losing heat through that wall in the same way, but you're definitely having airflow if things aren't designed well. And you don't want to be smelling other people's smells and having air movement if you don't have to. So, when you're designing a passive house in an ideal world, when you're starting from scratch, you have a lot of control over, you have more control anyway over things. Sometimes if it's an urban lot, you have less control. But certainly, if you have a naked piece of land and you're designing a passive house, you start with what is the shape of the building and what way am I orienting the building and how do I take advantage of the opportunities on the site to make the best of the physics basically. So you point it south, which is common sense and we've been doing for centuries, but when we have a building like this, we're starting from a little bit of a penalty in terms of trying to hit targets. So the design approach is quite different. So before I get into that, I'll just tell you, when we started this project, the first thing we did was have an inner guide audit, and we found out that the lower door tests the air tightness. There's 24 air changes per hour through this building, so that means we're totally going to benefit from fresh air, except for it's disgusting, so not really. Interestingly, so this house and the house next door were owned by the same lady, and she sold them at the same time, and so that house is also having a retrofit happening right now. And their blower door test was 34, so I feel like we got the better one.
And maybe to contextualize that for people who don't speak ACH,
yes,
an ACH rating of 24 in a house this size is about the equivalent of all the windows upstairs being open all of the time.
Wow.
And winter, summer, those windows are always open.
Yeah.
so yeah, I mean it was bad. It's just bad. A new build regular house is around, if your builder's relatively conscientious, it might be like a 3. An R2000 house is 1.5. And a passive house is aiming for 0.6 air changes per hour. Passive house retrofit gives us a little bit of help, and we only have to aim for 1. That's still a long way from 24. So starting with air tightness is like our kind of fundamental move, but it's not going to be the only thing that we can do to reach our targets. So in terms of energy, so in classic passive house, we have these energy targets that we're trying to achieve. So you have you're trying to heat the building, aiming for 15 kilowatt hours per meter square per year, which is kind of meaningless if you don't have a frame of reference, but a regular house might be 120. So it's about 80 to 90% better than in terms of the heating costs and heating energy than a regular house. So ours is 450 kilowatt hours per meter square per year. So the target for, the target is just like kind of hysterical if you think about trying to get there. Again, there are relaxations in passive house retrofits. And so a passive house retrofit is called an enerfit project. So I have used those interchangeably. To give you a sense of what that might cost us if we were to do nothing, which of course we're not going to do nothing. We had one power bill. I mean, we kind of set up the power and got a bill, and it was a couple $100s or something, and then we got another power bill and it was $2,200. And we thought the heat was all off, but there was one heater that was on 15 that didn't get turned off. And so the building was empty, there was nothing happening, the plumbing was off, we thought it was, so we definitely can't afford that. So we're gonna do better. Does everybody know what passive house is? Yeah, okay. So it's essentially a very low energy building that's designed using science. And so I talked about these targets. So we have targets for heating demand, which is the total energy that you use in the year to keep the building comfortable. There's also heating load. So that's the heating, the power needed on the coldest day of the year. So we have targets for that. And then we have the air tightness target. And then our windows have to be extremely great windows. So I'm not cooking you like this one keeps doing to my back. So in Canada, that means we need triple glazed windows. That is like one of the most fundamental critical things in the building, not just for performance, but also aesthetics. Like, it's really important. It was really important to us to not replace the windows in this building with vinyl windows. We really were looking for like the authentic wood. The other thing that you need is a really excellent ventilation system, because if we're successful, we're going to make this building, more or less completely airtight. And so to ensure comfort and health, we want to have an HRV, so a heat recovery ventilator or an energy recovery ventilator that also handles the humidity. And so that will bring out, flush out the kind of stale air and bring in fresh air, but it strips the heat out of the air as it does that. And in a passive house, that has to be 75% efficient or better. And most, everybody's house, if you build a new house, has to have an HRV now, but it's like maybe 50% efficient. So like that, 75 is or better is significantly, represents significant savings. For an enerfit project, there's, we still have targets, but there's two different kind of streams that you can approach the project. So with a passive house, of course, they're super insulated. They have way more insulation than a regular house. And when you set out to design a new passive house, usually you have your structure, and then you make the walls and the roof fat with insulation outside of that structure. And that's totally a valid approach for a retrofit, except when you have a party wall, you're on Falkland St and you're at 100% lot coverage on the neighboring side. So what that means for us is that we have to insulate to the inside. And when you're insulating to the inside, you're limited in that fatness. Like, it's like, if your kind of house is out in a field, you could put 2 feet, 3 feet if you wanted to of insulation outboard, but inside we're, at a certain point it's going to become, impact our use of the building. So what we're doing, and you start to see it in the downstairs, back corner, and a bit in the living room, we're making the walls, we're furring them out on the inside, but just kind of ever so much. So it's going to be, you might have noticed these walls aren't straight or level or plumb, but the new ones will be. And so it's going to be somewhere between like 7, 8, some places maybe even 9 inches of depth that we're installing to put new insulation in. And then we're using cellulose insulation to pack in those cavities. And we're using cellulose because it's a low-embodied carbon product. So something that is, embodied carbon or upfront carbon is really missing from the conversation in buildings and high-performance buildings even. So we've been very good and very focused on energy efficiency in Canada for a long time, since the 80s. But materials, like when they're produced or when they're harvested or, made out of, fossil fuels, they emit greenhouse gases throughout that kind of life cycle. And so what we're starting to see now that we have amazingly airtight and energy efficient buildings is that upfront carbon cost is actually more impactful in the total carbon footprint of that building than the energy that you've saved through energy efficiency measures. So if we retrofit buildings using products with high embodied carbon, then it could be decades before that is even made up in terms of the energy efficiency savings. Whereas cellulose is recycled newsprint, which basically used to be a tree. And so we're locking carbon in the form of that recycled newsprint in the building. And so we have a little bit of we won't have a completely negative carbon footprint, but by choosing that material as opposed to things like foam-based insulations, we are doing a better thing for the planet. And that's really important going forward, because in the next 10 years, the carbon emissions that we as a world emit are more important than the ones that are going to happen in 40, 50, 60 years of the building through using heating. So there's my lecture on carbon. So back to the ways that we model, we have to model the underfit retrofit. So the first way is called the energy demand method, and that's pretty simple. It is just that you kind of have the same kinds of range of parameters as a regular passive house. So you have a heating demand target, you have an air tightness target, and you have a primary energy target. So a primary energy target is, we don't just have energy that is used to heat the building, we also have computers and fridges and all of the other loads on the building that we pay for. And so in passive house, we have the heating target, but we also have the primary energy target. And in a retrofit, both of those are relaxed. So if you're doing the energy demand method. And those targets vary depending where you are in the world. So they also acknowledge that if you're in Halifax, it's gonna be way easier than if you're in Iqaluit. So for our building, our target is 25 kilowatt hours per meter square per year. It's still pretty far off of 450, and really the only way we could hit that target is if we were to fatten the walls on the outside. So moving on to the next method, which is a little bit more complicated. And so that method is called the component method. And essentially, the activity is the same, not when you are energy modeling. It's like the world's most boring video game, and then there's like sort of all of these parameters that you're toggling to try and achieve a target. And so you're always kind of, in a regular passive house project, kind of always, what if I make my windows better? What if I make my insulation a little thicker? What if I use a higher performance HRV? You're always kind of playing around with these variables to see what's most impactful. And also it's really helpful to play around with those to find out where you might be wasting money. Because when you take out a wall, you kind of add 2 inches of insulation, you've saved yourself money. Another 2 inches, you've saved yourself money. But once you've got to a certain point, you're just spending money and you're not saving any money. And so the model helps you find that kind of optimized point for the performance of all of the various components. So literally we're looking at, houses are complex, but we have to look at all of the various systems in the house and optimize all of them. So when we're doing that on a regular house, passive house, we are just kind of playing with all of those levers and looking at, am I hitting that 15 kilowatt hours per meter square per year for my heating demand? And am I hitting my primary energy demand? In the component method, each of the subcategories, so our walls, our windows, our ventilation system, they all have a kind of little sub-target. So instead of looking at what is the overall energy use, we're just going, okay, do the walls get close enough? Does the roof get close enough? And so that's It sounds more complicated, but it's the exact same work we're doing. We're just kind of looking at different ways of looking at it, I guess. And so for our building, what that means is that we've actually got it modeled so that's meeting the passive house EnerPHit target, but our heating demand is still like 52 or something like that. So it's still well above the 15 kilowatt hours per meter square per year. But heating demand of 52 when you're starting at 450 is like an 88% improvement or something like that. Like, it's pretty impressive. And it's definitely going to mean that we're not paying $2,000 a month for our electricity. And then on the system side of things, because I'm kind of talking a lot about on the system side, we're also going to use heat pumps. So this building actually was all electric when we got it. That's unusual, actually. Like, a lot of buildings in Halifax still have oil. We have one or two that we've renovated that still have coal infrastructure in them. So it was all electric, but it was just nasty baseboard heaters. So we are going to get our system that, we're the classic do not do in that we haven't designed everything yet. Full disclosure, sorry, Gav.
I know.
It evolves. Don't tell people that you're doing a retrofit, because then you might get swayed by their opinions. So, I was kind of all like gung-ho to like set out and buy like a super fancy HRV and get somebody to sponsor us. There are some amazingly efficient HRVs. But then as I was talking with, I was actually talking with a guy named Willem Painter who, he works for MCO, but he used to be Natalie Leonard's energy model. So he has done a bazillion passive house energy models. So I was like, what should I do? And he was like, if you're pairing it with a heat pump, and what our plan is, we don't want a lot of ducts in here. So our plan is to actually duct our mini split heat pump into the HRV, like, so that they're both in the same ducting. And he was like, yeah, it doesn't matter if you're doing that. Like, it's going to be just, the efficiency benefits of setting it up that way mean that you can buy a $1,000 HRV and kind of end up with the same heating bill impacts as $10,000 HRV. So yeah, so I mean, it was great that Gav's team set up the kind of side-by-side comparison downstairs of the Vata windows. So they are triple glazed, built in Poland, wood windows, FSC certified lumber, aluminum clad. They're beautiful. They're, they function amazingly. They're tilt-turned, so they lean in at the top where they open in like a door. So we have lots of control over the airflow in the space. And those guys had a cool lesson in how to adjust them. So, lots of times you get windows that are, most of the windows in my house just, there's like one corner that's slightly annoying. So they're fully, they're amazing windows. In terms of the performance, so they're triple glazed, and what that means is they have like a U value of 0.5 and also a G value of 0.5. So U value is the thermal performance. 0.5 is good. And the G value is the percentage of energy that is passing through the window that is benefiting you. And so when you order windows, a lot of times for passive house, you actually want to do a bit of an exploration about those specs and work with the company to tailor them to what you need them to do. So you can say if the windows, in our case, we just ordered all the same glass. It saves confusion sometimes, and it didn't seem to make that big a difference. If we had a wall of West glass, it probably would make a big difference. So if you go with a window with a higher G value, it lets in more heat, but it has a lower R value in that window, so it isn't as thermally good for you in the winter time. So you're sort of playing this game with the windows to figure out what's going to be best for your building. And often in our projects, what we find is that we need to use a low U value or a low G value on the north side and a high one on the other side of the building. And that means that you're losing less heat through the north, where you're not really getting, you get a little bit actually of solar gains somehow, but really it's not what you're going for. Yeah. We have other options for windows, but we've worked a lot with Beta. They do most of the buildings, they supply most of the windows for the buildings that we're designing now. There's also like really great local passive house quality windows available through Cold Tech. And we've used those on like projects with more of a budget, also sometimes in the past when the lead time was an issue, but now actually getting the windows from Poland is faster than getting the windows locally, which is just, who knows. But I haven't really talked about our, we need air tightness, but how are we going to achieve that air tightness and air control, and also vapor control. It's pretty humid in here, even on regular buildings, we need vapor control layers, thermal control layers, which we're doing with insulation, and air control. And the air, when I told you that, like when we modeled the house, kind of go through the process a little bit differently because there's things you have to do, and then there's the things that have variability. So like, I know we have to aim for 1 air change per hour. I don't know how thick at the start of the project the walls have to be to kind of get where I want to be. So the first move I made in the model, after being like, okay, here we are, we have 450 kilowatt hours per meter square per year as our heating demand. I went to the air tightness section at the model, and I changed it from 24 to 1. And the energy demand dropped to 233, just with that one move. So that's almost half, just through air tightness. So we want to put something inside it and seal it up, and particularly these control layers that we're relying heavily on for the durability and longevity. Like these things go to the longevity and quality of the building, not just the energy performance, because they're keeping the water out, keeping it dry. So we want to use something that's a little bit more robust and we know is going to last. And so a lot of these companies that have the smart vapor performance have proprietary tapes, and you really should use the tape that comes with that company just so that you know that it's compatible. Like if you kind of cherry pick and get the cheapest tape from that guy and the cheapest membrane from that guy, there's no guarantee that they're actually going to stick together properly. But there is the sort of workhorse of the tape world that everybody seems to be using in Nova Scotia on passive houses is the 3M air and vapor barrier tape. It's called 3015. There's another one called something with an 8 in it. And those ones, they've been I don't know, if you're really nerdy and read Fine Home Building or Green Building Advisor, they've done tape studies where they tape all the kinds of tape to all the kinds of substrates and see which one does the best universal job. And that 3M tape is one of the ones that sticks to everything quite consistently. And importantly for us, it does pretty well in shitty weather. So you can stick it when it's raining and not worry too much about it not sticking. So there's other sort of reasons why you might use a fancy tape. This one is when you're installing windows like that. So our window, I don't know if any of the builders in the room notice, but it doesn't have a brick mold or a nailing flange or anything. It's just a wood box. It's exactly like these guys, old school. And so there's lots of different ways to install those windows. Usually these ones come, you can see they install them with straps. That's what we usually do. But then it's going to get sealed to the membranes into the building with tape. And some of the tapes that have the kind of fold into a V and double split peel off can be really helpful in that application, to be kind of tape all the way around the window with one half and then position it in place and then pull off the thing. And so you're really, I'm sure you still stick tape to yourself, I would, but it definitely makes that job easier. So I'll toss that one around. And these tapes, I don't even remember what they do, but here's some more sticky tapes. I'll toss them around too. There's very specific tapes for very specific, one of those goes with that black membrane that's floating around. And yeah. My advice is it used to be like we would talk about these fancy types and fancy membranes, and they'd be like, yeah, if you mail to Germany and wait 2 months, you'll get them. But they're like 2 days away on a truck from Toronto. Like, we can get our hands on a lot of really high quality targeted passive house stuff. Again, you don't have to, but it can be a good way to kind of give yourself added insurance on some of the quality control stuff. Oh, how about the roof? Isn't our roof amazing? Yeah, there's some pretty interesting joinery in the roof, and obviously that gray area where there used to be a chimney. We don't know yet what we're doing with the roof. The long-term plan is to add a third story if, we don't run out of money and get too exhausted by that idea. He almost upsold us into doing it right now, but we chickened out.